Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture on control systems. In the previous lecture we have been studying this object called the observer, right, and we saw certain beautiful things about this observer. For starters, we saw that, well, in the presence of an observer, the closed loop poles of the system become those of the observer as well as those of the plant plus controller combination, right. So in other words, at least the location of the poles of the plant, they still continue to remain the poles of the closed loop system, okay. So the closed loop system continues to have poles at those same locations, right. In addition, you have some more poles that emerge due to the design of the observer, right. Now in today's lecture we shall start to answer we shall see the answer to another question which we sort of triggered in the last lecture. If you notice, the question was, okay, it's fine to say that the closed loop system has the same poles as the poles of the observer and the poles of the plant plus controller combination, but is it then true that starting from this reference input signal, yeah, to this output, if you look at the closed loop transfer function, does the observer play no part in this? Are we in other words saying that if the observer weren't present and if you were allowed to tap in those states from the plant itself and use them for feedback, for state feedback, the transfer function that we would have got, yeah, which is given by this, yeah, is this going to be the same transfer function that we will get in presence of this closed loop observer now, right. So in order to answer this question, let us take a look at this equation. I am going to start by rewriting this equation again, right. So at the cost of again repeating myself, let me write that equation. So this is x dot, this is x hat dot, where x are the states of the plant and x hat is the states of the, is a vector that contains the states of the observer, right. So if I recall, we had a here, we had bk here, of course we had x and x hat here. So x is an n tuple, x hat is also an n tuple, right, okay. And then we had, I believe, a minus LC here. If you do not recall this, please revisit the lecture, the previous lecture, and you would see that this is indeed what the transfer function was, or what the state space expression was. So a plus bk plus LC, right. So you see a plus bk plus LC. Now what I am going to do is, I am just going to, well, you can also write y is equal to, well, you know, c and 0 times x and x hat, yeah, because you are just taking the outputs of the actual states as your overall plant's output, right. We will see that later. So we have assumed that there is no d, yeah, so we are assuming that it is a strictly proper plant, so there is no feed forward, okay, right. Now what we are going to do is we are going to take the Laplace transform of this entire equation, yeah, on both sides. Let us see what happens then. So the first equation then, so of course as we do usually with Laplace transformed variables, we indicate them by capitally sized letters. So then we have a xs, of course this is s times xs, and this is a xs plus bk x hat s plus b rs. Subsequently we shall drop this argument in s for the sake of brevity, yeah, otherwise we will see that things soon start to get very big, the expressions start to get very messy, yeah. So we will better omit these arguments in terms of S and just use the capitalized letters to indicate that these are indeed the Laplace transform variables in S domain and not the time domain variables, okay. So this is my first equation. What about the second equation? By the same token, I can write the second equation as S x hat S is equal to minus LC xs plus A plus bk plus LC. Remember, these are constants, so the Laplace transform makes no difference, right? Yeah, plus B R S. So this second equation we can then in turn write as in the following fashion: Si, rather let me jump a step here and explain in words what I am doing here. So I am going to pull out this all x hat related terms to the left hand side, and that way I will get Si, because remember this is S times this means it is Si times this. Similarly I can also write Si times here, it really does not matter, right. So then I can write this as, because I have to get a matrix, no, S cannot be subtracted from a matrix, right. So it is Si, that is a very naive, very non-technical way of saying things, I understand, but still, yeah, it's useful to remember that, right. We've seen this already, that we write Si times xs or Si times x hat s instead of S times, yeah, right. So then this means that I can write Si minus A minus Bk minus Lc times x hat is equal to minus Lc times xs plus B times R, right. So instead of doing that I am going to in one shot take the inverse of that, and I am going to get the expression as minus Si minus A minus Bk minus Lc inverse times Lc xs plus again Si minus A minus Lc minus Bk inverse times B Rs, yeah. So I pull down all x hat related terms to the left, yeah, then the coefficient of x hat is Si minus A minus Bk minus Lc. So I am operating, I am hitting it from the left with the inverse of that jumbo term here, that is this term here, yeah, and then this is what I get. On the left hand side, that inverse pulverizes the original matrix, and on the right hand side I have this inverse and this inverse, yeah, it's just this inverse being plugged in here, yeah, this is with this minus sign intact. So let me call this as equation 2. Now what I am going to do is I am going to plug in this expression for x hat in terms of x in equation 1. In other words, I am going to eliminate x hat from the first equation using the expression for x hat I have obtained from the second equation. So you can easily imagine this is going to be a really nasty term, yeah, but do bear with me. So in the first equation, let me simplify that. First equation is Si minus A times xs is equal to, let me go a little slow, is equal to Bk times x hat. So as I said, I will get rid of this argument in terms of S, right. So when I write this capitalized x and x hat, you understand that it is the transform domain variables. So this is Bk times x hat plus Br is equal to Bk times x hat plus Br, yeah, this is another way of rewriting this 1, so let me call this 1a, yeah, and this 2, now I am going to plug this in here, this x hat. So let me substitute this x hat here, yeah, so this x hat I am going to substitute from 2. So then what do I get? I will get Si minus A times x is equal to Bk times, and hang on, there is this jumbo term coming up. So this is this, okay, minus of Si minus A minus Bk minus Lc inverse times Lc, if I am not mistaken, times x. That is the first term, yeah, I am going to just substitute for x hat. What is the second term? It is again this jumbo term, this inverse times B times R, plus Si minus A minus Bk minus Lc inverse times let us see, was this Br, yeah, times Br, and not to forget there is also this other term, right. So that will be descending from here, yeah. So I am going to substitute for this x hat here. So remember that this entire term, yeah, this entire term within the second bracket, yeah, within this brace bracket, this is nothing but x hat as I have substituted from here, right. So if this is x hat, now I can get this expression only in terms of x and r. So the idea is I want to see the transfer function from r to x. Once I have seen that, getting from x to y is nothing but multiplying by c, right, because I am not doing anything to the output, right. So I want to ensure that this is indeed not dependent on this observer that I have added. In other words, it is not dependent on this L and C, yeah. I want to ensure that this is now still the same closed loop transfer function that I would have got in the absence of the observer if I were allowed to tap in to the states of the plant in the first place, which of course I am not allowed to do now, which kind of necessitated this whole observer design. So now if we can do that, then we would be satisfied that this observer has silently done its job of kind of observing the states based on the output information without affecting the closed loop transfer function between this reference input R and the output, that is Y, yeah. So that is what we are keen to see. Now you might see that these lot of these inverses and all these terms, and you might wonder how are we going to deal with this, and I agree that maybe in most undergraduate level texts or courses these are not things that are dealt with, but once we are through with this, I assure you that it will not seem as intimidating as it seems now, yeah. At first glance now you will see there is this huge inverse term sitting here, right, Si minus A minus Bk minus Lc inverse, and it seems like it is impossible to get rid of Lc from here, right. But we will soon see that that impossible will eventually become possible. How so? So let me pull out this x related terms on the left hand side, yeah. So I am going to pull out this first term here, and I am going to leave the r related terms on the right hand side. So on the left hand side then I have Si minus A, let me put a third bracket, a box bracket, plus, remember there is this minus sign here, when I bring it to the left hand side it becomes a plus, plus Bk times Si minus A minus Bk minus Lc inverse Lc, this whole thing times x. Okay, why am I writing the s again? I do not need that, right. So I have pulled out all the x related terms on one side. Now it is the turn of retaining all the r related terms on the right hand side. So what is the first r related term? It is Bk times this jumbo inverse times Br. So I have Bk times this Si minus A minus Bk minus Lc inverse B. Okay, let me get rid of the B here, I can take the Br common outside, right. So this is going to be plus I, and I am going to have the Br outside, yeah, clear. This is this Br, no, so this Br times I is just this Br, right, and the second term is just this term that is descending here, yeah, that is this term, yeah, easy to see, although pretty messy to work with. And now I am going to claim something which at first glance might seem like wishy-washy, right, it is too far-fetched, and how are you going to deal with this. So here is what I am going to claim, and I am going to also prove this. So please make a note of this particular step here at this juncture, yeah, make a note of this particular step. We will revisit this, and now we will take some detour. We will take a detour and we will look into some results on matrices, yeah, and then we will resume on this. So in this one slide this following slide we are going to just take a closer look at this, and the claim is, I am going to make a claim here that this I plus Bk times Si minus A minus Lc minus Bk whole inverse, yeah, look, what do I want to do now? If I want to write r in terms of x, I had better hit both sides with the inverse of this fellow. Yeah. So if I get the let me use a different color, maybe this color, yeah. So if I hit both sides, if I pre-multiply both sides with the inverse of this fellow, on the right hand side at least I will only have br, on the left hand side I will also accumulate something even jumbo beyond this, right. Seems like still very messy, but things have a way of working out, as we shall see. So now my next idea is, can I obtain the inverse of this term? Yeah, so that is my goal. Can I obtain an inverse of this term? If I can, of course by that I mean in a closed form. Of course given any matrix you can obtain its inverse, but that is not fun. Fun is when you can express it in terms of these same variables, these same matrices, right. So can I obtain an inverse of this boxed term here? If I can, then I can hit it with that inverse on both sides. Of course on the right hand side I know that it will just pulverize this term. On the left hand side I might have a simplified expression for this if I obtain an inverse in the closed form, right, and that is what we are going to see in this form of this detour here. So I am claiming that this inverse, and pay very close careful attention, is going to be nothing but I minus, note that the sign changes, right, the sign changes, I minus this bk remains as it is. What happens inside the bracket is this bk vanishes from this bracket here, yeah. So this vanishes and this sign changes, those are the two changes that happen, and that is it. So I am claiming that this is true, right. Now what happens if this is true, how does it help, we will see later as we resume our calculations from here onwards, but as of now this itself seems like magic, right. How is it even true? So in order to see this, there is only one way of proving it. So we have to show that this is true. If this is a claim, then we have to show this. So if we have to show this, then we better hit both sides with this term, yeah, and if we can end up with identity on the right hand side as well, then we would have proved this. So let us say we pre-multiply with this, so we get identity is equal to I plus bk, so we have to show that, so ought to show that, so we have to show that this, or that is equivalent to showing that I plus bk times si minus a minus lc minus bk whole inverse times I minus bk times si minus a minus lc whole inverse, yeah, that is what we have to show. If this is true, just notice one more time, if this is true, then let me hit with this term sans the inverse, let me hit with this term on the left of both sides. So if I hit with this term on the left hand side, pre-multiply, yeah, you can pre-multiply, post-multiply, whatever, but I am going to pre-multiply. So I am going to hit with this term on the left, I am going to get identity here. On the right hand side, if I hit with this, this is what I get. So I have to show that this is indeed, this right hand side, this nasty expression is indeed equal to identity, right. How can I show that? So that is, in order to that we have to show that I is equal to, now let me just openly multiply this, So first time I multiply this with this, I get identity, next I multiply this with this and I get minus bk times si minus a minus lc inverse. Then I multiply this, let me use a different color, then I multiply this with this, yeah, and I get plus bk si minus a minus lc minus bk whole inverse, and finally the biggest and the nastiest term apparently, right. So that is when I multiply this with this, then what do I get? I get plus bk times si minus a minus lc minus bk whole inverse times bk, of course because there is a minus sign here, this sign changes to minus, yeah, this sign changes to minus, right. So we have this minus sign here, and let us resume. Then we have this followed by that is si minus a minus lc whole inverse. huge terms, right. But one glimmer of hope is that now we have to show that, of course this we can cancel out, so we have to show that, that is in order to show that, let us take the plus sign on one side and the minus, okay, yeah. So what we will then do is we will take from the left hand side to show that 0, the 0 matrix is equal to, let me take the bk common from the left, not just the bk common from the left, but let me do something else. Let me take bk times Si minus A minus Lc minus bk whole inverse common from the left. What will I then have left? I will then have left, now notice what about this term, how do I recover this term, yeah, or rather let's start with the simplest term. So this is identity, this is identity. What about this term, how do I recover this term? I have to clearly multiply by this Si minus A minus Lc minus bk times Si minus A minus Lc inverse, right. You see now the first term, when this I multiply with this, I get back this term, then I multiply this term with this term, so this inverse and this they pulverize each other, so I am left with bk times Si minus A minus Lc, yeah. So that is just a second, yeah, so this term, sorry, this term is basically this term, no, this and this. Now this term if I have to recover, then I have to actually multiply with this, so Si minus A minus Lc minus bk inverse times Si minus A minus Lc minus bk, so they pulverize, so it remains is this bk times this, so that is basically this term, no. So this term is accounting for that, right. Now I am left with the last term, so the last term is nothing but again a minus sign, so this much is already taken out common from the left, so what I am left with is bk times Si minus A minus Lc whole inverse, yeah. Let me go to the next slide, but do well to recall. What I am now going to do is I am going to take out this part common from the right, but of course this fellow does not have it common from the right, so if I take it out common, then I have to multiply it with the original term, because this is the inverse I am going to take out common. So you understand that this identity now I am going to write as Si minus A minus Lc times Si minus A minus Lc inverse, like this, right. So then all the three terms have Si minus A minus Lc inverse common on the right, because remember in matrix multiplication common from the right and common from the left are different, yeah, I cannot mix them up, the matrix multiplication is not commutative, right. So therefore what I am then required to show is to show that 0 is equal to this bk times Si minus A minus Lc minus bk inverse, bk times Si minus A minus Lc minus bk whole inverse, yeah. Then notice very carefully, what I am now going to do is I am going to keep this term, so I am going to retain this term, so I have rewritten identity as Si minus A minus Lc times Si minus A minus Lc inverse, that is how I am going to rewrite identity here, and then I am going to take this part out common from the right, because this part is common here, this part is common here, and this part is common here as well in all the three terms, right. So I am going to just take it out common, so what I am left with now in this case is Si minus A minus Lc, so what I will have is Si minus A minus Lc, what I am going to be left with here is minus Si minus A minus Lc minus bk, so let me put a bracket, minus Si minus A minus Lc minus bk, yeah. What about the last term? I am going to take out this common, so what I am going to be left with is a minus bk, yeah. So it is just a minus bk, and then I will have this Si minus A minus Lc whole inverse, yeah. I have taken it out common, see I have done no extra jugglery, okay, it is simple straightforward, I have just taken something out from the common from the left, something out common from the right, so that whatever is inside is free from those inverse related terms. That is the trick. This will work in many other cases as well, as you go into multivariable controls or proving a lot of stuff in robust control, yeah, in obtaining transfer functions. This is one trick that will always help you in so many different ways, right. Anyway, so what then we are left with is this bk, to show that bk times Si minus A minus Lc minus bk whole inverse. What is left here in this brace bracket? Si minus A minus Lc minus Si plus A plus Lc plus bk, and of course then a minus bk. So you see everything cancels out just as we want it to, Si minus A minus Lc inverse. So you see this bk and bk cancel out, this A and this A cancel out, this Lc and this Lc cancels out, and last but not the least the Si and the Si also cancel out. So you are left with a big 0 in the middle. So this is obviously true, or to show that the 0 matrix is equal to the 0 matrix, which is obviously true. But having shown this equality 0 is equal to 0, what have we actually established? Remember, keep track of that. What we tried to show was initially this expression. So each of these steps we can reverse, right. So now we can go in reverse order. We can start with 0 matrix is equal to 0 matrix, then from 0 matrix we can say that this is equal to this, right, and we can retrace our steps. Each of these steps are reversible. Nothing we have done that prevents us from going in the reverse direction of logical progression, right. And therefore we end up with the result that this I plus bk times this whole nasty fellow's inverse, and then the whole inverse, the inverse of the whole fellow, is nothing but just this term. Okay, so we have proved this. That is what we set out to prove, and now we are going to make very handy use of that. So now we are going to hit, as I said, now go back to the starred expression, yeah, and we are going to hit with this inverse on both sides. So now resume the original calculation, okay. So this is a resumption. The last couple of slides was just a proof of an ancillary result. So now we resume what we were doing. So what we are doing is basically we are saying that Si minus A plus, so let me just adjust this here, let me again do a small bit of a trick here. Si minus A minus Lc, yeah, I am going to just add Lc and subtract Lc from this, and it will be clear in a while why I am doing this. So I am just going to take Si minus A minus Lc, and I am going to just add a plus Lc, and you will immediately see what happens then, yeah. Then you will have bk times Si minus A minus Lc, let me see, minus bk whole inverse times Lc, minus bk whole inverse times Lc plus Lc. So this plus Lc and minus Lc I am adjusting here, yeah. So this times, this whole thing times x is equal to, what have I written here, bk times Si minus A minus, yeah. So this, let me just leave a br over here, it is as if I have already hit with this inverse on both sides, yeah. So what I am saying is I am hitting with this inverse on both sides, so I am only left with br on this side. So then I better account for this inverse on the left hand side as well, right. So I have that whole fellow's inverse. But what do I know about that whole fellow's inverse? I am not writing that expression, that whole fellow here, but I am just going to in the next step write what that expression of the inverse is from this what I have just derived. So this inverse is nothing but I know it is I minus bk times Si minus A minus Lc inverse, yeah. So then br is I minus bk times Si minus A minus Lc whole inverse times Si minus A minus Lc plus, now notice what am I going to do here, I am going to combine these two terms here. So there are a few tricks here, small little tricks here, but if you follow them you will see what is being done here. What I am going to write is I plus bk times Si minus A minus Lc minus bk whole inverse times Lc, and then the third bracket, right, times x. Now the fun starts. What is the fun? You see I have br on the left hand side and I multiply this I times this, right. So what do I get? So I get Si minus A minus LC, yeah, that is this with this, then I have I with, but and then I have got this term with this term, yeah. So that leaves me with Bk only, minus Bk, yeah. Next what I am going to do is at one go I am going to multiply this whole term with this whole term, and notice that this is exactly its inverse, yeah, the inverse of this fellow is this. So this is going to give me identity times LC, right. So there I have plus LC. Notice very carefully, what is this term? This term is nothing but the inverse of this term, right, and where is this term sitting now? This term is now sitting pretty over here. So when I multiply this overall whole term here, so first I multiplied this term with this term, that resulted in these two, yeah. So when I multiplied this whole term with this term, I got this much, and then I multiply this whole term, this entire term with this term, of course followed by LC. So this and this pulverize each other because they are inverses of one another, as we have just proved. So all that you are left with is just this LC times X. But what is this? This is plus LC and minus LC. So you just cancel them out. And then what we are left with is Si minus A minus Bk times X. So therefore what I can now write is X is equal to Si minus A minus Bk whole inverse times Br. Therefore Y is equal to Cx is equal to C times Si minus A minus Bk whole inverse times Br, thereby telling me that this is my closed loop transfer function. And if this is my closed loop transfer function, this is exactly what I wanted, bingo, right. This is exactly where I want it to be. You see, it is independent of this observer that I have designed, independent of those gains, those L's and the C term that enters here, right. This is only dependent on the gain that I have designed for the controller. So the presence of the observer does not affect the closed loop transfer function from the reference input to the overall output, okay. So that is the beautiful thing. Of course there might be some disturbances. In that case things become a little more complicated, but that you can take as a homework to see if there are certain disturbances at the output of the plant, what is the transfer function from that disturbance to the output, right. Again you will have to make liberal use of these sort of identities like these, right, how to invert matrices like this and so on and so forth. So sometimes you have to make use of these to simplify the terms. When all seems hopeless, yeah, and meaningless, then you have once in a while these sort of identities that help you massage your way through and get some tractable expressions, yeah. As you have now seen here, we have got this transfer function, the closed loop transfer function. We managed to prove to you that not only are the poles of the controller and observer, not only can they be designed independent of one another, but the fact that the observer does not make its presence felt insofar as the transfer function from the reference input to the output is concerned, yeah. So that is one of the greatest achievements, now you can safely say, of modern control theory, because now you no longer are dependent on having to tap in to the states in the middle of the design of the plant in the wiring, right. All that you need is access to the output and the input channels of the system which is like a black box, and then you can design a model of the system, and using the model of the system you can now design this observer. From that observer you extract the states, which you always can, because after all this is just a model which is a piece of code for you, and then using those estimated states x hat you design a state feedback, and those states x hat will eventually converge soon enough to your actual state values x, even if your initial estimates are not exact, because of the fact that your observer poles have been placed suitably on the LHP and suitably farther away from the imaginary axis, so that your observer's error, yeah, the error variable, that is x minus x hat, converges to 0 soon enough, right. So that is the whole idea behind this observer design. So now this joint observer and controller design helps you in designing a state feedback control action. So that is one form of controller synthesis technique that we have now learnt using this modern control theory, and hopefully one that you found to be impressive enough. If not, we will now take an example. In fact, we will take the very same example that we had motivated a few lectures back and shown you that not only can you not get suitable or desirable performance out of that system using any classical control technique, but you cannot even stabilize that plant, right. But now we will see that by the power of this modern control theoretic tool, that is this combined observer and controller design, having access to only the input and output suffices for you to be able to design a control action such that you will not only be able to stabilize it, but you can place your poles at any location that you like. Be aware, however, that shifting the zeros of the closed loop transfer function still remains a problem, and if you are not convinced about the fact that, well, the zeros cannot be arbitrarily placed even if your poles can through state feedback, here is a little bit of, so I mean that's, I do not want to sort of leave you with the impression that, well, all the problems have been solved, right. There is still this problem that you cannot place the zeros, the closed loop zeros, you can place the closed loop poles, well, at least not independently. So suppose there is no D matrix, you see now what happens is in the closed loop system, this is your transfer function, right, sorry, not this, excuse me. So this is now your transfer function, alright. So remember that the C matrix has not changed, the B matrix has not changed, the only thing that has changed is basically this A matrix. And how has this A matrix changed? Well, for that, if it is a controllable system, go back to the controller canonical form, the phase variable canonical form. So you will see that your ACL will now look something like this, you will have 0 1 0 0 0 0 0 1 0 like this till you have the ones, and then finally you have minus A0 plus K1 minus A1 plus K2 likewise till minus AN minus 1 plus Kn. This is going to be a closed loop A matrix. Your B closed loop is going to be the same as your B, which is going to be nothing but 0 0 0 0 1 like this, and your C matrix is again going to be nothing but the same as your C open loop, right. It is going to be the same C1 C2 dot 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 till Cn, which is nothing but the original C matrix that you started off with, alright. So now you notice that what is the zero structure affected by, if you now study the phase variable canonical form, you will see that the transfer function, the open loop transfer function would have been something like, if I am not mistaken, C1 plus C2s plus C3s squared plus dot 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 till Cn s to the power n minus 1, divided by A0 plus A1s plus dot 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 till An minus 1 s to the power s to the power n minus 1 plus s to the power n. So this, you see, the entries of the C matrix are basically what determine the zeros. Now this is your open loop transfer function, right. So what is your closed loop transfer function by analogy? After all that changes is this, no, this A0 changes to A0 plus K1 minus A0 plus K1, right, this A1 changes to A1 minus K2, so likewise only these terms change. So your closed loop transfer function will still have the same zero polynomial, you can take this as an exercise to convince yourself that it is indeed going to be so. So this is what happens, at least insofar as the controller canonical form or the phase variable canonical form is concerned. But then we know that the transfer function is invariant to similarity transformation. So if through controller design in the phase variable canonical form the zeros are not affected, then you go to any similarity transformed representation of the same transfer function and you will end up with the same zeros, right. So therefore we see that even though the poles can be placed at will, the closed loop zeros remain the same as the open loop zeros. Of course, if you had a D matrix, things would have been slightly different in the sense that you would then have y is equal to Cx plus du, and remember this u always contains Kx plus R, right. So then you would have had the overall closed loop C matrix change to, it's pretty straightforward, right, C plus D times K, yeah. So then you might say, well, hang on, if you had the D matrix, if you had a biproper transfer function, then of course the C matrix changes and the zeros change, right. I have two things to say to that. One, firstly, it's rare to find biproper transfer functions, okay, you may not agree with that, that doesn't sound very mathematical, okay. What if you do find a biproper transfer function? Then it seems like your zeros are affected by the gains that you choose, right. But here's the second deal, which kind of is a deal breaker in that sense, right. It tells you that, look, you have chosen this K not to design the zeros but to design the poles. Once you have placed your poles, the K is unique, as we have seen earlier, right. The K is uniquely determined by what you desire your closed loop characteristic polynomial to be. Once you fixed up that K, the CCL, the closed loop C matrix, gets fixed up automatically. So you have no independent freedom, or you have no independent way of assigning the zeros. Now whatever zeros you get with that chosen K, you have to live with it. So although the zeros will change from their open loop locations, but these are still arbitrary. In fact, for all I care, these zeros could actually go to locations that are more undesirable than in the open loop case, and then you have nothing to do about that, right. Because once you have fixed up your K to get suitable poles, you cannot redesign your K again to get suitable zeros. If you do that, you will be moving your poles, right. You have only n parameters to play around with, and those will allow you to assign only n poles, right. You cannot expect to now assign those n or n minus 1 n zeros in this case, it is biproper, right, if it is D. So if you cannot now hope to again reassign both your poles and zeros using the same vector K, right. So I want you to be aware of this, that this is a limitation, that although things might seem like, okay, we have done quite a lot and we have achieved quite a lot, at the same time the fact that even with this state feedback, with this observer and everything, you still aren't able to place the zeros. And why could the zeros be potentially a problem? You see, when you have right half plane zeros, right, those are things we don't like. They are somewhat akin to some time delays, right. We have seen that a Padday approximation of a time delay, yeah, e to the minus st, we often get a Padday approximation like 1 minus st by 2 upon 1 plus st by 2, right. So this is like a time delay, isn't it, this sort of a Padday approximation, and you see this is tantamount to a non-minimum phase system, a right half plane 0, right. So if you have a right half plane 0, well, tough luck, it seems like there is nothing much you can do independently. Once you have chosen your K to assign your poles, you have to live with whatever zeros that come as a combined package with it. You cannot assign it, reassign it independent of the pole locations, right. So that is one slight catch which we cannot address using linear time invariant control action, right. There is something called periodic control, which is tantamount to sort of sampling this continuous time system at a very fast rate, yeah, at the input, and at a different sampling rate at the output, yeah, right, and then converting it to a discrete time equivalent, yeah, it does work. We will not get into that because this course does not talk about discrete time control, digital control, right. If you do a course on digital control and come back to this problem, and you can read up some papers that appeared in the early 1990s, right, you will see some papers on periodic control where they talk about this discretizing this system into a discrete domain system, right, discrete time system, and then in the discrete time domain using some different rates of sampling, you can trick the system into thinking, yeah, you can trick the system into thinking that although the continuous time systems poles are in the right half, the zeros are in the right half plane, the corresponding discrete time systems zeros, yeah, so the continuous time systems right half plane matches with the discrete time systems unit circle, yeah, outside the unit circle. So just like we say that for a continuous time system we want all our poles to be in the left half plane, in the discrete time domain we want all our poles to be in the interior of the unit circle, right. That is a well known result. Anyway, we have not discussed it, it is just some sort of a nugget that I am dropping here, right. So you will see that using this some technique called periodic control, what happens is that you manage to trick the system into believing or behaving as if the discrete time system's 0 is still inside the unit circle, although the continuous time, the corresponding continuous time systems 0 is on the right half plane, right. But unfortunately those are not really linear time invariant control strategies, yeah, so those will not come within the purview of whatever we have covered here, right. So that I hope summarizes the controller and observer, joint controller and observer design technique. Now as promised, I will take up a numerical example, so I have got it worked out here so that I do not have to spend too much time on calculations. I am probably going to cheat a bit, but you should carefully do these calculations and convince yourself that I am not making any calculation errors here in this, right. So here is the transfer function that we shall take up as promised a few lectures back. So let us say you have the transfer function which is given by s upon s minus 1 times s plus 5 times s plus 4, yeah, which is nothing but, typically this is a very convenient form to handle. Here you can actually see what the poles and zeros are, but typically what people you are most likely to encounter is a transfer function given in this form, yeah, that is when you do not really know what the poles are, right, plus 11s minus 20. This is essentially the same polynomial, by the way. I am just writing it in this form so that the poles are not explicit from the way it has been represented, right. So this is the transfer function, and let us say I want to, so look, we have already seen that for a transfer function such as this, the root locus tells us, go back a few lectures and you will see that we have illustrated this through a root locus sketch, that neither a proportional controller nor a proportional derivative action can ever stabilize this plant, right. So then what do we do, what option are we left with after all, yeah. So here is what we are going to do, we are going to use state feedback with an observer. So first at a rudimentary stage we will do well to design the state feedback control action independent of the observer. As we have seen already, see this is the beauty, we have already seen that we do not need to care about the observer when we are designing the controller's gains, and we do not need to bother about the controller's gains when we are designing the observer's gains, right. That is the separation principle, that well known separation principle at work, which allows us to design both of them independent of one another. So of course given that I have been allowed the choice to represent this in any state space depiction possible, and if I want to design poles, then let me just design it in, let me just represent it in the phase variable canonical form. In many cases you will be given an ABC matrix, ABC triplet, yeah, maybe not a D because this is a strictly proper transfer function. So in many cases you will be given the ABC matrices and you will have no choice over the realization. But suppose I am given this choice to realize it in any form I like, I am going to just realize it in the phase variable canonical form, right. And in the phase variable canonical form, it is very easy to see that these coefficients will appear in the last row. So I will write this as, immediately you see I can write this as this form, I know what it is going to look like, 0 1 0 0 0 1, and what about the last row? Well, this minus of minus 20, that is 20 is going to appear here, minus 11 is going to appear here, minus 8 is going to appear here, and then this is x, plus of course this b also I can blindly write, I know what it looks like in phase variable form. And then of course y is equal to 0 1 0, right, because you see what are the coefficients. So starting from the constant term, there is no constant term here, 0, the coefficient of s is 1, the coefficient of s squared is 0, of course the coefficient of s cubed will not appear in the C matrix, it will appear in the D matrix if it were present, but since it is only s here, so the question of a D matrix does not arise, yeah. So this is a convenient representation, I can immediately read off, yeah, once you have found out how to represent in the phase variable canonical form, this is very standard way of representing it. Please practice problems, the more you practice the more readily you will be able to read off, and given any transfer function by inspection you will be immediately able to write down, as I did here, what the phase variable canonical form realization would be. Now if this is my phase variable canonical form, suppose somehow, now you might ask who has told me where to place the poles, well we do not really know, right. For now, for the purpose of your exam or for the purpose of your understanding, you will have to assume that someone has told you that this is where the poles ought to be, right. If you learn linear quadratic regulator theory, LQR, optimal control, then you will understand that this can be chosen, the where to place the poles is a critical question that can be answered by the optimization of some cost function, yeah. You want to optimize the energy spent, yeah, so you put some weight on the amount of control effort you are applying, yeah, and you want to put a weight on your state values, yeah, you do not want your states to be very far away from the 0 value, right. So that is how you, or your desired values, so x minus xd, you penalize any deviation of the state from its desired values, yeah. So that is how you choose some cost function. Anyway, that is again beyond the purview of this, yeah, but this is what we are going to say. So suppose we want arbitrarily, just like that, it could be any value, we want poles at let us say minus 10, minus 20, minus 30. So remember, the open loop system has poles at 1, minus 5 and minus 4, and I want them to be placed at minus 10, minus 20, minus 30. Clearly, again to reiterate, the root locus based method will fail here. You will not be able to design any P or PD controller that will allow you to design your poles in this fashion, yeah, right. So this is where we will really hit at this point, that the very fact that you are able to do this, where the root locus based method of designing the classical control method will fail, yeah, this will kind of really give you that realization that this works, this modern control theoretic method works. So how do we approach this? This is very simple here, yeah. What we basically then want is our desired characteristic polynomial is s plus 10 times s plus 20 times s plus 30, which if I am not too mistaken should look something like, hang on, yeah, I have probably computed it here. So it is going to be s cubed plus 60s squared plus 1100s plus 6000, yeah. Just check that this is my desired closed loop polynomial. So therefore, what is my desired ACL? So see, if I am given this, all of this in the phase variable canonical form, this is all very easy, it is too easy, right. This ACL is going to be, then the desired ACL is going to be 0, 0, 1, and the last row is going to be filled up with, well, I have minus 6000, minus 1100, minus 60, minus 6000, minus 1100 and minus 60. I hope I have not goofed up. So what is this ACL? ACL is going to be A plus BK, and I know A and ACL, I know B, the only thing I need to determine is K. So you see, I have 0, 1, 0, 0, 0, 1, minus 6000, minus 1100, minus 60 is equal to 0, 1, 0, 0, 0, 1, and the last row now is the interesting bit. I have 20 plus K1, you can check, so B times K, so K1, K2, K3, so 20 times K1, yeah. So I have K1, K2, K3 minus, okay, plus 20, this is minus, hang on, what was it, minus 11, minus 8, and minus 11 and minus 8. So then I can just equate these three terms, right. It is minus 6000 is equal to K1 plus 20, minus 1100 is equal to K2 minus 11, and minus 60 is equal to K3 minus 8, yeah. So this leads me to conclude that K1 is equal to minus 6020, K2 is going to be equal to minus 1089, yeah, and K3 is going to be equal to minus 52. So basically my control strategy U is going to be minus 6020, minus 1089, minus 52 times x, that is my desired answer, right. Now you might say I had it easy here, right, you might say I had it very easy here, I just chose it in the controller canonical form. What if this was not given in the controller canonical form, what if it was in some realized in some other form? Here I had the choice of realizing it in any form, so I chose it in the phase variable canonical form, right. So well, to reiterate, there are two methods of doing that. One, you could have gone on from that control, that arbitrary form of realization to this controller canonical form realization or the phase variable canonical form realization, gotten these gains here, and then through that similarity transformation, that T inverse that I just showed you, which is basically nothing but the CC times C inverse, yeah, like we derived a few classes back, and then got back the gain in terms of the original states, yeah, that is one method. The second method is something which I personally prefer for such smaller systems, because it avoids the complication of having to invert the controllability matrix and find that similarity transformation and all that. So that second method is just simply equating the coefficients on both sides, yeah, but I will not solve that for this case. What I will do is, when we come back for the next lecture, remember we have just what we have done up till this point is we have merely solved for the controller part, but we have to still design the observer, right, and as we have claimed that the observer can be designed independently, right. So we will design that observer. When we design that observer, you will see that what is a blessing for us when designing the controller is no more a blessing while designing the observer. What I mean by that is that this controller form lends itself very easily to the, this controller canonical form lends itself very easily to the design of a controller. But if I now want to design an observer, yeah, it is not so straightforward, right, it is not so straightforward as just equating 3 coefficients and getting those 3 equations and from the 3 decoupled equations, right, 3 variables from the 3 decoupled equations. So there we will have to equate the closed loop characteristic polynomial, yeah, and because the observer and controller design processes are just duals of one another, very simple, except that A plus bk and there you have A plus lc, right. So you can look at it as A transpose plus C transpose L transpose if you like, either way, yeah, it is just the same, the controller design and observer design are just the same, only thing is that you need to be able to represent it in the observer canonical form. But while designing the observer, what we shall do is we shall do no such thing again. So that is a method that is always there, right, you can always take a system, take it to its controller canonical form, design the controller gains and then get it back in terms of the original system. Similarly, you can take any arbitrary realization to its observer canonical form, then get the observer gains in that observer canonical form and then revert it back to its original form through a suitable similarity transformation. But we will not adopt this method at all. You can practice this method, you will see a lot of examples in standard textbooks adopting this method, but what I prefer personally is, once I have ascertained that the system is indeed controllable and observable, I am guaranteed that a solution exists for this choice of k or this choice of L. If a solution exists, then I might adopt any method, I will get to the same solution after all, because this is a seesaw system and the solution is unique, right. So then why bother with all those inversions and all, just equate the coefficients for small systems up to 3 cross 3 or maybe even 4 cross 4, just equate coefficients of the characteristic polynomial, yeah, in the closed loop characteristic polynomial with the desired characteristic polynomial, just equate coefficient wise and you will get n equations in n unknowns, the unknowns being either the controller gains or the observer gains, and you would have solved your problem, right. So we will exactly follow that method when we come back for the next lecture. The same system we will design next an observer, so that the observer, because remember this system, the A matrix is going to be not Hurwitz. So if you design an observer without compensating for these eigenvalues or these poles of this system, yeah, the observer, even if you have small mismatch at the initial instant between x and x hat, that is the estimated states, they will tend to blow up and your x hat will never converge to x, and if you are trying to feed back that x hat and hoping to stabilize this plant, it will never work out. So you need to stabilize, you need a closed loop observer, you need some suitable L matrix or L vector, yeah, to sort of assign the poles of the observer very deep into the left half plane. There is, however, something that I must mention at this point, yeah. In general, the poles of the observer should be much further into the left half plane than the poles of the controller. Why so? Because remember, after the error in the observer has converged to 0, it is only then that we have close to actual states being estimated, right. The error in the observer decays means that x hat is almost equal to x. So if the dynamics of the observer is not significantly faster than the dynamics of the plant plus controller, yeah, then the states that we will be thinking of using, that is the x hats as the proxies for the actual states, may not already have converged, the error might not have converged to 0 already. So in general, The good idea is always to place the observer poles much further, much deeper into the left half of the S plane than the poles of the controller, and this is not a problem because after all the observer, as I said, is a software, it is a piece of code. So, there is no real actuation as such going on over there. So, you have no hardware to take care of, right. So, that is one thing. And before we conclude, I would, although I have put in enough effort into deriving all of these today, but I would like to really leave something as an exercise, maybe not completely as an exercise, but I would invite you to consider this, that for the observer and controller combination, the dynamics that we considered, yeah, it was also a state space representation. So, what were the A matrices? The A matrix was A plus B K, let me go back a little, yeah, just where I had written that equation here, yeah. So, you have A and you have B k and you have minus L c and A plus B k plus L c, right. So, let me go back to this, yeah, sorry, yeah. So, what we have here is again A B k minus L c A plus B k plus L c, right. This was our A matrix, the overall system matrix. The B matrix was B and B, yeah, for the 2n cross 2n system, right, the states of the actual system and the states of the observer. And the C matrix turned out to be in our case C 0. Now, think of something called similarity transformation, yeah. So, what if I choose a similarity transformation such that I use I minus I 0 I times A B k minus L c A plus B k plus L c times I 0 I. Now, I leave it to you to, it is a trivial exercise to check that this and this, these two matrices are inverses of one another. So, technically I can call this as T inverse and I can call this as T. So, this is of course the same dynamics, so it is just a similarity transformation, but look what happens then. I minus I, so A minus L c, so that is A plus L c, and then the next part when you add you get B k minus, yeah, so it is minus of A plus L c, and here you of course have the second row intact L c and A plus B k plus L c times I 0 I, yeah. So, then you see that what you will get is of course A plus L c, and the next one is 0, and then you have minus L c, and finally again you have sorry, what was this, A plus B k, A plus B k. So, now from this, if you are a little familiar with eigenvalues and eigenvectors or eigenvalues of rather diagonal or block triangular matrices, you would immediately see that indeed the eigenvalues of the overall 2n system, the 2n state system, are nothing but the eigenvalues of A plus L c and the eigenvalues of A plus B k, that is the controller and observer poles sitting together. If you want to push this a little ahead and also do the check, then what is C t, rather not this C, but the overall C t. So, let me modify that, yeah. So, if you do this C 0 times t, what is this? Just take the C 0 and post multiply it by t. What you get is essentially C and C, yeah. And what you get as the overall B, which is T inverse times B B, yeah, that is this matrix times B B. So, of course, the first entry will become 0 and the later entry will be B. So, now notice that this is now your overall C matrix, this is now your overall B matrix, and this is now your overall A matrix. So, then if you are trying to find out the overall transfer function, that will be C, C, because under similarity transformation the transfer function does not change, as we have seen so beautifully, right. S I minus A minus L C 0 and minus L C and S I minus A minus B K, this whole fellow's inverse times 0 B. And now again I am going to, at this point I am going to leave one homework for you. Already we have proved this with a lot of headache and all, but this is actually simpler because we are now taking just similarity transformation, a very special choice at that. So, now what I am going to claim is that, look, this is block triangular. The only thing I am not going to prove here is that the inverse of a block triangular matrix would also be block triangular, provided the matrix is invertible in the first place at all. Yeah, please check that as a homework. It is not very trivial, but nonetheless, once you agree that the inverse of this fellow is also going to be block triangular, and what's even more interesting and important is that the blocks sitting at these diagonals would be the inverses of these individual entries. So, then if you post multiply it by 0 B, you are basically picking out the second column only, and the second column means 0 S I minus A minus B K is inverse, and from the first one you just pick out C C. So, this will eventually lead to C S I minus A minus B K inverse B, which is exactly what we had claimed in our lecture today. Yeah. So, the next lecture we shall actually go ahead and design the controller, but hopefully with this little bit of an exercise, there are a few gaps I have deliberately left in this proof. I leave that to you as an exercise, but you know, at least you have learned about two methods of proving the separation principle, and also of seeing that the overall transfer function does not change by use of the observer.